Welcome to this explainer, Order Out of Chaos, the switch statement in compiler design. If you're a college student studying computer science, or really, even if you just have a passing interest in how the software we use every single day actually gets built, the word compiler can sometimes sound, well, a little intimidating. It kind of evokes these images of incredibly dense, complex systems parsing through thousands and thousands of lines of code. But today, I want us to take a breath and just slow down for a minute. We're going to explore a remarkably elegant, peaceful solution that's tucked right away inside compiler design. We are going to look at how we can bring absolute order out of chaos using something you're probably already super familiar with, the switch statement. So sit back, relax, and let's untangle this together.
Think about what a compiler actually has to do for a second. It literally needs to read a source code file, character by single character, across thousands, sometimes millions of characters. Now, when a human reads a novel, we have the luxury of context, right? We easily remember the plot, the chapter we're in, the emotional tone of the paragraph. It's totally effortless for us. But a compiler? It is totally blind to absolutely anything except the exact character immediately in front of it. So how does it track its state without completely losing its mind? How does it remember if it's currently reading a variable name, a number, or just a comment, without getting utterly confused by the very next character it sees? That gentle curiosity right there is our starting point today.
Section 1. The reading process, navigating the automata. Let's dive in. To make sense of an endless stream of characters, compiler designers rely on theoretical machines to process text. Instead of trying to look at the whole document all at once, the compiler uses a beautifully simple concept called a scanner. This scanner reads just one piece of input at a time and reacts to it. The map it uses to navigate this whole process is called a finite automaton. It's represented by these minimal, elegant circles. In compiler construction, this is known as a deterministic finite automaton, or a DFA. Think of it a bit like a vending machine on campus. You're in a resting state, you insert a coin, and the machine clicks into a new state, just waiting for your selection. Here, each circle is a state. Imagine the compiler is currently resting in that far left circle. It reads a character, let's say a less than symbol. It gracefully glides along the arrow to the next state. From there, if it reads an equal sign, it flows to another state, recognizing a less than or equal to operator. Every single state has a unique, predictable transition based strictly on the single character it just read. There's no panic, there's no looking back. It's just a calm step forward based on incredibly clear rules.
Section 2. The tangled if statement trap, messy code reality.
Now there is very often a gap between the pristine elegance of a theoretical model and the messy reality of actually writing the code to make it work. When programmers try to translate those beautiful circles and arrows using ad hoc brute force coding methods, well, chaos ensues. We end up with a wildly complex block of nested if statements. Take, for example, an ad hoc implementation of a scanner trying to read a comment block. You might have an if checking for a slash, then another if tucked inside that checking for an asterisk, and to handle the loop of actually reading the characters, the programmer introduces a Boolean variable, a flag called done, and sets it to false. Then comes a while loop with even more if statements packed inside it, just hoping to eventually flip that flag. You've probably written code exactly like this at 2 in the morning for a CS assignment, where you're forced to hold the entire state of multiple variables in your working memory just to read the thing. It creates a stressful, tangled web. The crucial point here is captured perfectly by Kenneth C. Loudon when he notes, "Notice the considerable increase in complexity and the need to deal with the loop by using the Boolean variable done." When you're a student trying to build a compiler, or honestly any large-scale software project, relying on ad hoc flags like done or is finished or has seen asterisk quickly turns into a waking nightmare. As the number of states in your design rises, this brute force approach becomes incredibly difficult to read, debug, and maintain. The elegant flow of our circles and arrows is just completely lost in a sea of nested brackets and Boolean flags.
Section 3. The calm switch statement, a peaceful remedy.
But listen, we really don't have to live in that chaos. Let's shift our tone back to a peaceful resolution here. There is a far, far better way to implement these machines that completely preserves the elegance of our original theory. If we compare the two approaches, on one hand, we have the nested if and while loops. They're ad hoc, highly complex, heavy on those Boolean flags, and incredibly prone to errors. But on the other hand, we have our peaceful remedy, the doubly nested case statement. It is organized, highly predictable, strictly state-based, and features incredibly clean logic. Instead of juggling multiple variables, we use one single variable to maintain our current state. It acts as a calm, organized set of sorting boxes for all of our logic.
Let's actually break down how this builds into practical application. The logic of the doubly nested case statement breaks down into 3 low-pressure, totally digestible steps. Step 1, an outer switch statement simply checks the current state you are in. Step 2, an inner switch statement looks at the exact next input character. Step 3, based entirely on those 2 pieces of information, you assign a new value to your state variable and you switch gracefully to the new state. That is literally it. No Boolean done flags, no deeply tangled while loops. These 3 steps mirror the finite automaton diagram perfectly. You are quite literally just coding the arrows between the circles.
Section 4. Simplicity in compiler design, reducing cognitive load. This brings us to a fundamental philosophy that goes way beyond just writing scanners. Often, when we're learning advanced computer science topics, there is this massive temptation to write the most clever, intricate code possible. But actually, scratch that. As we've seen from the source material, the most effective implementations are actually the ones that reduce our cognitive load. True optimization isn't about complex hacks. It is definitely not about stringing together a fragile web of if conditions. It's about organizing your logic so that it remains simple, predictable, and completely manageable. The switch statement implementation teaches us a really vital lesson here. Replacing chaotic, scattered flags with strict, state-based simplicity brings absolute peace to our code bases. When your code actually reflects the clean structure of the underlying theory, bugs have nowhere to hide. And adding new features? It becomes a relaxing exercise rather than a stressful chore. I want to leave you with this final peaceful thought. We've seen exactly how compilers use states and switch statements to make sense of millions of characters without breaking a sweat. So how can you apply this exact kind of state-based simplicity to untangle complex problems in your own projects? The next time you find yourself tangled in a massive web of variables and if statements, just pause and ask yourself, what are the actual states of this problem? Can I draw the circles, map the arrows, and just switch gracefully between them? Thank you so much for taking this time to explore the quiet elegance of compiler design with me. Happy coding, and remember to keep it simple.